Good day to you all. I hope you are all safe and doing good. It's a privilege to meet you once again. Today is actually going to be our last session for the chemistry practicals. And today we're going to look at titration. So our last set of questions from the core chemistry practicals is based on titration. That is question 19, question 20, question 19, question 20, and then question 21. Okay, now before we start looking at the questions, I want to explain some few things concerning the setup for titration. So if you are looking at titration setup, Okay, so in a titration setup, these are the various apparatus you come across. I think in our previous questions we came across this apparatus. We call this pipette. So this is the pipette. You all know what this is. So this is a retort stand. Now this apparatus is what we call burette. This one is the burette. So this apparatus is what we call burette. So we have pipettes and then we have burette. Take note of the spellings. And then we have this as the tap. Then this one is the conical flask. Conical flask. Now the conical flask is placed on what we call white towel. So this a white towel. The normal towel, white towel. Okay, and then titration setup for core science is actually involves an acid-base titration. So this is a setup for acid-base titration. And most acid-base titration, what is in the burette is the acid. So usually what is in the burette is the acid. So this is the acid. And then what is in the conical flask is the base. So what is in the conical flask is the base. Let me rename this, label it well. So this is a white towel. And then the solution in the conical flask is the base. And the solution in the burette is the acid. Now if the curved surface area here, the same thing, curved surface area here, is what we call the meniscus. So this one, the curved surface area there, we call it meniscus. Okay. Let me space that so that you can see properly. So you have the meniscus, and then the solution in the burette is what we call the acid. So that's the acid. So acid. Okay, so please take note. So the curved surface area there is the meniscus. We have two solutions. One is in the burette, one is in the conical flask. In an acid-based titration, the acid is usually in the burette, and then the base is in the conical flask. Now, what's the use of this pipette? The pipette is what is used in taking and transferring the base into the conical flask. So this base was actually pipetted, or was taken by the pipette, and then before it was transferred into the conical flask. So if, for instance, the volume of base used in the titration is, let's say, 25 cm cube. 25 cm cube. Then you use a 25 cm cube pipette. It will be indicated on the pipette that the volume is 25 cm cube. So using the 25 cm cube pipette, you take the 25 cm cube of the base, and then you can put it in the conical flask. Okay. During titration, the volume of the acid used is actually read on the burette. There are readings, there are scales on the burette. So during the titration, the volume of the acid that is used can be determined by reading the value on the burette. Okay, so these are some apparatus, or this is an acid-base titration setup. So acid-base titration setup. Let me view acid-base titration setup. Okay. The tip of the burette, we call it the delivery bulb. So delivery bulb, we say delivery point. Okay. So these are some parts or label parts we come across in a titration setup. Now, so I've talked about the function of what? The partet. That one is used for taking and transferring the base into the conical flask. Now the burette here is to contain the acid. So it's used for containing and delivering the acid into the conical flask. The tap here is control, is to help control the movement of the acid from the burette into the conical flask, And then what is the role of the white towel here? You see, during the titration, we have indicators used, and in the process there's a color change. So the white towel there is to help you identify when there is any letter color change. So it helps in identifying, it helps to identify any color change. As part of the retort stand, we have the clamp also attached to it. So there's a clamp here. So what is the function of the retort stand and the clamp? Is to hold the burette firmly in position and also to give support to the conical flask. So that's the function of the retort stand and the clamp. Holds the burette firmly in position and also gives support to the conical flask. So these are some of the label parts of an acid-base titration setup. Okay. Now, based on that, let's start looking at the related questions under titration. The first question there is question 19. Question 19. It says that the figure is an illustration of a setup for carrying out an experimental process in the laboratory. Dilute hydrochloric acid and sodium hydroxide solutions were used in the experiment. It says study the figure carefully and answer the questions that follow. Okay, so question A says, or question I says, name the process illustrated above. So so the setup there is similar to what I've drawn here. And he says that you should name the process illustrated above. So this is acid-base titration. Or simply put, you can just write titration. So the process is titration. Okay. So acid-base Titration. If you simply write titration too, you'll be given the full marks. Now, II alpha. II alpha says, name the parts labeled I, IV, V, and VI. So you are supposed to name the parts labeled I up to VI. So the part labeled I is the burette. So that's the burette. Now the II is pointing into the solution in the burette. And I told you usually the burette contains the acid. Now if you look at the information from the preamble, it says dilute hydrochloric acid and sodium hydroxide solutions were used in the experiment. So the burette contains the acid. So from the two solutions given, dilute hydrochloric acid is the acid. So the II is dilute hydrochloric acid. Now III. So your II is the top. Is the top. The IV is the conical flask. Conical flask. The V is the white towel. White towel. White towel. And then your VI is the retort stand. Okay, so these are the various parts of the setup. Now the beta of question I says, which laboratory apparatus was used to introduce the sodium hydroxide into the part labeled IV? So even if you didn't know that the dilute hydrochloric acid was in the burette, from the beta, is saying that the apparatus that was used to introduce the sodium hydroxide into the part labeled IV. It means that the IV, which is a conical flask, contains the sodium hydroxide, meaning that the solution that will be the burette will be the hydrochloric acid. So I told you that for you to transfer or introduce the base into the conical flask, you make use of what? The pipette. So the question is asking that what apparatus was used to introduce the base, that's the sodium hydroxide, into the conical flask. So the answer is pipette. Pipette. Okay. Question I alpha. It says name the type of reaction that occurs in the part labeled IV. So an acid-base reaction, a reaction between an acid and a base, actually to form water and then salt, is called neutralization reaction. We looked at neutralization reaction in theory when we were talking about acid, bases, and salts. So we say a reaction between an acid and a base to produce water and salt only. That reaction is what we call neutralization reaction. Neutralization reaction. So I. So the reaction is neutralization reaction. That is I alpha. And then the beta, it says that write a balanced chemical equation for the reaction that occurred in the part labeled IV. So the reactions between the hydrochloric acid and the sodium hydroxide. Hydrochloric acid is ACl. Sodium hydroxide is NaOH. You form sodium chloride and then water. Hydrogen is one here. There's another one making two. Hydrogen has two. Chlorine is one. Chlorine is one. Sodium is one. Sodium is one. Oxygen is one. Oxygen. So that's a balanced equation. That's the balanced equation. And then the last question here, IV. It says that name one indicator that could be used in the experiment. So you are talking about acid-base titration indicators. So acid-base indicators. You have phenolphthalein. Please take note of the spelling of phenolphthalein. Phenolph. So phenolph and then phthalate. So this is the spelling of phenolphthalein. Take note. Students write it and then they make mistakes. So please take note of the spelling. If your spelling is wrong, you'll be marked wrong. So take note of the spelling. And then the second one is methyl orange. We have other indicators, but these are the commonly used indicators. The phenolphthalein and then methyl orange. You are supposed to write one, but any of them that you write will be correct. So that is for question 19. Question 19. Question 20 is similar to this. So you're going to quickly look at question 20. Question 20. Question 20. Question 20. There's no so much difference between the question 19 and 20. So you have the diagram given. The question says, the diagram below is an illustration of a setup for carrying out an experimental process in the laboratory. Study the diagram carefully and answer the questions that follow. Question A says, name the process the setup is used for. So just like question 19. So this for titration or acid-base titration. And then question B says that name each of the parts labeled I to IV. So you have I, and then you have the IV. So your I, in this case, the retort stand. And then the II is the burette. The III is the top. And the last one, IV, is the conical flask. conical flask. Question C. Question C says, which laboratory apparatus was used to introduce the sodium hydroxide into the part labeled IV? So the same, just like the previous one, this is a pipette. So the pipette is what is used to introduce the base into the conical flask. So pipettes. And then the last question here is question D. Question D says, write a balanced chemical equation for the reaction that occurred in a part labeled IV. So from a diagram, you have the reactants or the solutions given. You have the sulfuric acid in the burette, and then the sodium hydroxide in the conical flask. So the reaction between sulfuric acid is A2SO4, and then sodium hydroxide, that is NaOH. Your process, sodium combined with the sulfate, you have sodium sulfate. And then when the H here combines with the OH, you are forming water. To balance, sodium here is 1, sodium here is 2, so we can put 2 here. If you do that, it affects oxygen and hydrogen. So oxygen here is 2, oxygen is 1, so you put 2 here. The hydrogen here is 2. This 2 is affecting hydrogen. Hydrogen also 2. So you have 2 plus 2, 4. And then the hydrogen is 2 times 2, 4. We have only 1 sulfate. Sulfate here is also 1. So that is a balanced equation. That's the balanced equation. And that is all for question 20. Question 20. Now the last question under titration is the question 21. Question 21. In the first 2 questions, question 19 and 20, they are straightforward. There was no calculation here there, but for question 21, there's a calculation. There's a calculation. So you take a critical look at the question 21. Question 21. So question 21. It says that the figure below illustrates a setup for the titration of 0.2 molar hydrochloric acid against 25.0 centimeter cube of a solution of sodium hydroxide. It is important for you to take note of the statement. 0.2 molar hydrochloric acid against 25.0 cm cube of solution of sodium hydroxide. The question continues by saying that study the figure carefully and answer the questions that follow. The AI says name the parts labeled I up to IX, and the II says state one function of the parts labeled III, IV, and VII. So let's look at question A. We're supposed to label the part from I to IX. So you have I, IV, V, VI, VII, VI, II, and then we have the IX. The I is the curved surface area. Okay, the curved surface area is the meniscus. Meniscus. And then you have the II, that is the solution in the burette. The solution in the burette, as I said, is the acid. So that would be the hydrochloric acid. And then the III is the burette. The IV is the tap. The V is the conical flask. The VI is the white tar. The VII is the solution in the conical flask. So that's the base. And the base here is sodium hydroxide. The VII is the retort stand. And lastly, the IX there is the delivery bulb. Okay, so these are the label parts of the AI. Now the II, question AII says, we should give one function of the parts labeled II, IV, and VII. So for III, the III is what? The burette. So what's the function of the burette? So as I said, the burette is used to contain the acid and to deliver the acid into the conical flask. So it is used to contain the hydrochloric acid and to deliver it into the conical flask. So that's the function of the burette. So it's used to contain, or it contains the acid and it delivers it into the conical flask during the titration process. You're also supposed to give the function of IV. Your IV there, the IV is what? The tap. So what's the function of the tap? I told you the tap controls the movement of the acid in the burette into the conical flask. So it is used to control the amount of the acid that enters into the conical flask at a time. So that's the function of the tap. Controls the amount of acid that moves from the burette into the conical flask. Then the VII. You're supposed to do a function of VII. VI is the retostant. Retostant. I told you earlier on that the retostant, the clamp, helps to hold the burette firmly in position and also gives support to the conical flask. So it helps to hold the burette firmly in position, and also gives support to the conical flask. Okay, so that is the role of the retostant. Now the question B. Question B. Question B says that you should write a balanced chemical equation for the reaction that takes place between the hydrochloric acid and the sodium hydroxide. So you're writing a reaction between the ACl, that's hydrochloric acid, and then the sodium hydroxide, NaOH. You've come across this reaction. That was in the first question, question 19. You have sodium chloride and then H2. You cross check, everything is balanced there. So the reaction is balanced. Okay. So that is for question B. Now question C is where we have the calculation. So this is an important question to look at. In the previous questions, there was no calculation. So it is important that you take a look at the calculation. It says that assuming the volume of acid is 28.0 centimeter cube, calculate the number of moles of the sodium hydroxide in 100 cm cube of the sodium hydroxide solution. Okay. Now, if you go back to the preamble, we were given the concentration of the hydrochloric acid. That is, it says that the setup is for titration of 0.2 molar hydrochloric acid against 25 cm cube of a solution of the sodium hydroxide. So it means that in the titration process, the concentration of the acid is 0.2 molar, and the volume of the base used in the titration is 25.0 cm cube. Now, the question is asking in C that if the volume of the acid that was used in the titration is 28.0 centimeter cube, you should determine the moles of the sodium hydroxide in 100 cm cube of the sodium hydroxide solution. So we have the concentration of the acid. We also have the volume of the acid used. So using the concentration and the volume, we can determine the moles of the acid used. And then from the balance equation, you can compare mole ratios, and then you obtain the mole of the base that was used during the titration. So the first thing is we're going to look for the moles of the acid. From the information we have, concentration of the acid, the ACl. Concentration is the C. Specifically, that's the molarity. It was given as 0.2 molar. We also have volume of the acid. That's the V. The volume here was given as 28.0 centimeter cube. 28.0 centimeter cube. Your volume should be in dm cube, so we divide this by 1,000. And when you do that, that will give you 0.028 dm cubes. So that's the volume of the ACl. So we can calculate the mole of the ACl, mole of ACl. Mole of ACl. How do you calculate for the mole of ACl? We know from theory that concentration or molarity C is mole over what? Volume. So if you make N the subject, your mole becomes the concentration times what? The volume. The concentration times the volume. Okay, so using N equals C times V, we calculate for the mole. So mole of the ACl is equal to the concentration of the ACl times the volume of the ACl. The concentration is 0.2 and then the volume is 0.028. If you multiply this is giving you 0.0056. So this is the mole of the ACl. Okay. The question is asking us to find the mole of the base. The mole of the base. The reason why we could not calculate the mole of the base using concentration times the volume is this. We know the volume of the base that was used in the titration, but we were not given the concentration of the base. So you can't use this approach to calculate for the base. But from the information given, it is the mole of the acid that we can calculate. So after getting the mole of the acid, we now come and use the mole, the balance equation, and we compare the mole ratios to obtain the concentration of the, to obtain the mole of the base. From this reaction, the mole ratio of the ACl is 1. The sodium hydroxide is also 1. The NaCl is also 1. The water is also 1. I told you that when you balance an equation, the figure in front of the compound is the mole ratio. If there's no figure, then the mole ratio is 1. So if you look at this, there's no value in front of the ACl, so the mole ratio is 1. This one to there's no value, so the mole ratio is 1. This one to no value, the mole ratio is 1. The H2O2, there's no value, the mole ratio is 1. What does it mean? It means that if, for instance, there is 2 here, if there is 2 here, then the mole ratio of the ACl becomes 2. Okay. So yeah, because there is no value, the mole ratio is 1. So we are supposed to look for mole of the base NOH. That's what we are calculating. But from the equation, well, let me just omit that. I told you that if you are supposed to look for mole of a compound using the equation, the one that you are looking for will be above, and the one that you know will be below. So I'm looking for this one. So this one will be above. And then the one that you know the mole of the ACO, so that will be below. Then you equate it to their respective mole ratio. The mole ratio of the base is 1, the ACL is 1. So mole ratio of the base, NOH, is 1. That of the ACL is also 1. Okay, I'm looking for what is above. So I just take this one, the one that is down, to go and multiply the ratio. So I have the mole of the sodium hydroxide to be equal to 1/1 times the mole of the ACO. 1/1 is 1. The mole of ACO is 0.0056 mole. So the answer is 0.0056 mole. Okay. Now, some of you may be tempted to think that this is the final answer. But if this is your final answer, then you are wrong, because of the earlier statement. The question says that the moles of sodium hydroxide in 100 cm³ of the sodium hydroxide solution. But if you look at the initial preamble, the preamble says that the titration involves 0.2 molar hydrochloric acid against 25 cm³ of solution of the sodium hydroxide. It means that the volume of the sodium hydroxide used in the titration is 25 cm³. So it means that this mole that we have obtained here is present in the volume that was used in the titration, which is the 25 cm³. But the question is asking you to find the mole in 100 cm³. So for you to do that, use simple proportion. That is, if 20 cm³ of the sodium hydroxide is giving you this mole, then the 100 cm³ of the sodium hydroxide will give you what mole. So we use proportion in this case. So let me write, say from, there's no space here, so let me kind of continue here. Let me see. So, as I said, from the preamble or information provided, (25.0 cm³ of the NOH was used during the titration. So if 25 cm³ was used during the titration, then it means that the mole we have calculated is actually present in this 25.0 cm³. So we use proportion. So 25 cm³, 25.0 cm³ of the NOA solution is giving you 0.0056 mole. So therefore, it implies that what 100 cm³ of the NaOE solution will give you what mole. So this, the 100 multiplies this, and then the 25 divides. So you have 100 cm³ times 0.0056 mole over the 25.0 cm³. The cm³ cancel out, and then your final answer there will give you 0.0224 mole. So it means that this is the mole of the sodium hydroxide that will be present in 100 cm³ of the sodium hydroxide solution. So it implies that the mole of NOH that will be present in 100 cm cube of NOH solution is equal to 0.0224 mole. Okay, so that is the mole that will present in the 100 cm cube of NOH solution. Now, so please, if you indicate this as your final answer, this answer is wrong, because this is the mole that is present in the volume that was used in titration, and the volume used in titration is 25 cm cube. If the question has the question stated that calculate the number of moles of sodium hydroxide present in 25 cm cube of the sodium hydroxide solution, then this would have been the answer. But because it is stating a volume which is different, a volume which is different from the volume that was used in the titration, then proportion has to come in, because the mole you are calculating here is the one that is present in the volume used in titration. So using proportion, as we've done here, you obtain the volume that was actually used in the 100 cm cube of the solution. Okay. Let's look at the D part of the question. The D part of the question says that it should state 2 precautions to be taken when carrying out an experiment with the setup illustrated above. So in this, you are supposed to make sure that your burette and the conical flask are firmly held in position. So that is one. And then the other thing is the tap. You have to make sure that the tap is tightly fixed, because if the tap is not tightly fixed, immediately you pour the acid in the burette, it will drain into the conical flask. So you are supposed to ensure that the tap is tightly fixed. And then also when you are filling the burette with the acid, you are supposed to make sure that no air bubble is trapped in the delivery bulb. If you have some of the acid or air bubble dropped or trapped in the delivery bulb, it will affect the titration results. So you are supposed to ensure that when you are filling the burette with the acid, no air bubbles or drop of acid is trapped in the delivery bulb. Okay, so those are some precautions you're supposed to take note of. So precautions, or D, you're supposed to give the precautions. So the first one, the burette should be firmly held in position. Why is that? Why should that be done? If the burettes these are glassware, so if it is not held in position, it will fall and to break. And then if the acid is already in it, it will result in spillage. So should be held firmly in position to prevent breakage and spillage. And then the second thing is that I said the tap should be tightly fixed. The tap should be tightly fixed. So the tap should be tightly fixed. Okay. And then 3, the tap should also be regulated so that during the titration, only a small or a little amount of the acid is allowed to into the conical flask at a time. If you don't regulate the tap, you may end up missing the end point. So during titration, a little amount of the acid is allowed into the solution in the conical flask, and then it is well shaken. It is well shaken. So this is very important. The tap should be properly regulated to allow a little amount of the acid to enter into the conical flask at a time during the titration. If you just open the tap and all the acid drains into the conical flask, you miss the end point. So you have to make sure that a little acid is allowed into the conical flask during the titration. And then, as I said, when you are filling the burette, you have to ensure that no air bubble or drop of acid is trapped in the delivery tube. So that's the last one. Ensure that no air bubbles or droplets of acid is trapped in the delivery bulb when filling the burette with the acid. When filling the burette with the acid. You are supposed to give 2 precautions. So these are some of the precautions that you should take note of. And then the last question here, E, it says that what will be the effect on the titration result if droplets of acid are found in the space labeled IX? In the space labeled IX, that's the delivery bulb. So I said initially, if you have air bubbles or droplets of acid trapped in the delivery bulb, it will affect the titration result. How does it affect the titration result? It will end up increasing the titer value, that is the volume of acid that was used in the titration. So the presence of droplets of acid or air bubbles in the delivery bulb will end up increasing the titer value, that is the volume of acid that was used during the titration. So the E, question E. Question E. The presence of droplets of acid in the part labeled IX will increase the volume will increase the titer value. The titer value, that is the volume of the acid used during the titration will increase. Okay, so that is the effect. So it is not just a droplet of air, a droplet of acid. If the air bubbles are also dropping there, to affect the titration, the titer value. How does it affect the titer value? It increases it. So it will slightly increase the titer value. The titer value there is the volume of the solution in the burette, and the solution in the burette is the acid. So if the titer value is increased, it means that the volume of the acid will increase. The volume of the acid used will increase. Okay, so please, this brings us to the end of question 21. In fact, question 21 is more involving as compared to question 19 and 20. So take good look at question 21. This one involves the functions of some of the labeled parts. It also involves precautions that are taken, that should be taken during a titration process. Okay, so please take a very good and critical look at question 21. This brings us to the end of titration, and for that matter, core chemistry practicals. In our next section, we're going to start looking at practical questions under core biology. So I'll be posting some PDFs of the questions we'll be looking at. Now, I've answered most of the questions. Because of time, I've answered most of the questions under the biology practical. So from the PDF that I'll be posting, the questions that I've not answered, those that have not been answered, they are the ones that we will look at, we'll be going through in class. So on this note, today's class is amicably urgent. Stay safe and make sure you continue to study diligently in anticipation of your final examination.